Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shahinda Sadikin. So today me and my friends will be presenting to you about our second experiment, which is the single stage compressor. So for the introduction of this experiment, in this experiment, the performance of a single stage compressor is investigated with particular focus on its heating characteristics and heat loss behavior. A single stage compressor is a mechanical device that converts input power into kinetic energy by compressing and pressurizing air. These compressors are commonly used in applications requiring relatively low pressure. Understanding how quickly the compressor heats up and how it dissipates heat under steady state conditions is essential for evaluating its efficiency and operational reliability. So the objective of this experiment is to determine the rate at which a single stage compressor heats up during operations and to analyze the heat loss characteristics of the compressor under steady state conditions. So for the scope of this experiment this experiment is limited to the study of a single stage air compressor operating under controlled laboratory conditions. The analysis focuses on temperature variation over time and heat loss at steady state. Factors such as environmental conditions, measurement accuracy, and operating parameters are considered within a defined range. The study does not cover multiple compressors or extreme operating conditions beyond the experimental setup.
So for the theory part, a standard single band compressor function is to compress the air inside it and to measure the parameter of the output air. So this operator is used to show the relationships between the pressures, volumes, and the temperatures. Besides, it also demonstrates the conservations of energy, where in this case the energy is transferred to the output air. So in a standard single step band compressor, which is in figure 1, a fixed amount or volume of air is trapped between two sliding bands driven by an offset rotor. So it is then pushed to the outlets while the area is reduced. So its pressure is thus higher and is squeezed out of the outlet ports. When the pressure becomes the highest, and the temperature of the output air also increase according to the ideal gas law. So this heat the air consider the heat loss to the surroundings. So therefore, it is important to include this steady state heat loss of the compressors into the energy balance. So for the steady state process, indicate the rate of the heat transfer and the work crossing the control surface area are constant with time. So by using this formula, or total input energy equal to the total output energy, so the steady state heat loss of this compressor can be analyzed to find out whether its process is considered a steady state to ease out the calculation of parameter of the output air. So this one is our figure 1, and we need to determine the specific volume through flow meters, which is the B naught. And in order to calculate the specific volume through flow meter B naught, the pressure and the temperature units need to be converted into the kPa and Kelvins respectively. So the volumetric flow rate is equal to B inch divided by 60 times 10 to the power 3, and the mass flow rate is equal to the volumetric flow rate divided by the specific volume through flow meter. So the energy into the air compressor has heat and power out of the motor and the heat emitted by the compressor.
This figure show about our experiment setup at its core as single stack compressor. Next, figure show the descriptor of single stack compressor. The first, the air enter from air flow meter to inlet pressure control valve. After that, in pregnant chamber 1, the air pressure and the temperature were detected. The electrical motor connects the compressor. The result of electrical motor have spring balance and need to adjust until arm is horizontal. And the air pass through compressor to enter pregnant chamber 2. The outlet air pressure and the temperature were detected. Finally, the air exit from outlet control valve. This is our methodology. The power was switched on. Green and valves were fully open. The valves were turned and the clockwise opened it. All parameters listed in table 1 were recorded at the beginning of the experiment. Tachometer was used to record the motor speed and the motor was switched on. The compressor outlet pressure P2 was set to 1 bar gauges using the red outlet valve. The valve was turned and clockwise to increase the pressure. The spring balance was adjusted to ensure that the indicator on the motor was between the two red line periods to recording any motor force values. The temperature of the outlet air T2 was recorded at 1 minute interval using the stopwatch, and the two consecutive readings were the same. So before we stop the experiment, the compressor outlet pressure P2 were reduced to 0 bar gauges using the red outlet valve. The valve was turned anti-clockwise to decrease the pressure, and the motor and power was switched off.
Assalamualaikum warahmatullahi wabarakatuh. Now, I will present the result obtained from the single stage compressor experiment last week. Okay, first, referring to the table 1, the room temperature is 29 degrees Celsius and the air temperature entering the compressor T1 is 28 degrees Celsius and the initial outlet temperature T2 is also 28 degrees Celsius. And then the atmospheric pressure is 1.024 bar and compressor operate at motor speed of 1412.2 rpm with an electric power input of 1500 watts. And then the flow rate is 180 liter per minute. And then if we look at the table 2, the outlet temperature T2 over time at 1 minute interval at time 0, the temperature rise significantly to 75 degrees Celsius, that showing the compression immediately increase the air temperature. As the time progress, the temperature continues to increase steadily. For example, at 10 minutes, the temperature reached 51 degrees Celsius. At 20 minutes, the temperature increased to 183 degrees Celsius. And finally, at the 35 minute, the outlet temperature reached at maximum, which is 207 degrees Celsius. So from this trend, we can observe that temperature increased rapidly at the early stage of the experiment. Then the rate of increase gradually slowed down. So the behavior indicates that the compressor is approaching a steady state condition where the rate of heat generated and heat loss become more balanced. So moving on the table 3, which is so the energy added to the air by the compressor has C and the heat emit from the compressor QC over time. So at the very beginning, at 0 second, the energy added to the air is 163.77 watt, while the heat emit is significantly higher at 489.07 watt. This indicates that initially a large portion of the input energy is lost as heat to the surrounding. As the time increased, the energy added to air increased steadily. For instance, at 600 seconds, it reached 435.10 watts and is continued increasing until it reached approximately around 634.70 watts at 2100 seconds. And then this increase is due to the rising outlet temperature, which is result in a greater enthalpy change of the air. In contrast, the heat emit from the compressor show a continuous decrease over time. It can reduce from 489.07 watt at the start to 216.8 watts at 600 seconds and eventually drop significantly to only 17.2 watt at 2100 seconds. So this trend occur because at the beginning, there is a large temperature difference between the compressor and the surrounding, causing the high heat loss. As the system heat up, this temperature difference decrease, leading to reduced heat transfer to the surrounding.
As for the discussion, it requires us to discuss the shape of the graph that we obtained. So for the first graph, the shape of the heating curve, which is T2 versus time, shows how the outlet air temperature increases as the compressor operates. The graph represents a typical heating curve where the temperature increases rapidly at the beginning due to the heat generated during gas compression. As time progresses, the rate of temperature increase becomes slower because some of the heat is lost to the surroundings. Eventually, the curve begins to level off, indicating that the system is approaching a steady state condition where thermal equilibrium is nearly achieved. However, the absolute temperature values are higher than theoretical expectations due to an incorrect outlet pressure setting, which is the P2 equals to 1.4 bar instead of 1.0 bar, which shifted the curve upward. As for the graph 2, the graph illustrates a continuous increase in the energy added to the air over time, although the rate of increase gradually slows down. The graph indicates that the energy supplied to the air increases as time progresses because the compressor continuously performs work on the gas. However, the rate of increase gradually decreases due to heat losses to the surrounding environment. Eventually, the system begins to approach a steady operating condition where the energy supplied to the air and the energy dissipated to the surroundings become nearly balanced. The higher outlet pressure used in the experiment also contributed to an increase in the calculated energy input compared to the expected theoretical case. For graph 3, the graph indicates a gradual decrease in the heat released from the compressor as time increases. The graph shows that the heat emitted from the compressor is relatively high at the beginning due to the large temperature difference between the system and its surrounding. As time passes, the amount of heat released gradually decreases as the system moves closer to thermal equilibrium. Eventually, the heat emission becomes nearly constant when the compressor reaches a more stable operating condition. The elevated temperature readings due to higher outlet pressure may have increased the initial heat loss rate due to a larger temperature difference with the surroundings. The second discussion that we need to discuss is the energy that is being input to the system when the system is heated up. So the first is energy input to the system during heating. When the system is heated, the compressor continuously supplies energy to the air by performing work on it. The graph of energy added to the air versus time shows a steadily increasing trend, indicating that work is continuously done throughout the experiment. As the air is compressed, both its pressure and temperature increase due to compression effects. The mechanical work done by the compressor is converted into the internal energy of the air, which results in a rise in temperature as reflected in the heating curve. At the beginning of the experiment, the rate of energy input is relatively high as the compressor starts operating in the system rapidly warms up. However, as time progresses, the rate of increase becomes more gradual because a portion of the supply energy is lost to the surrounding environment as heat, reducing the net energy retained within the system. The incorrect outlet pressure increased the compression work required, resulting in higher energy input compared to the theoretical case. The second one is energy loss as heat. Not all the energy delivered by the compressor remains within the system. Some of it escapes to the surroundings as heat due to thermal losses through the compressor body and the surrounding air. This loss of energy is shown in the graph of heat emitted from the compressor against time. The elevated temperature due to higher outlet pressure may have increased the rate of heat loss, particularly during the initial stage of operation. The third discussion is to discuss the amount of energy that lost as heat as compared to the first one under the two conditions, which is the first one, the work input compared to the work input to the compressor. The work input to the compressor represents the total mechanical energy supplied to compress the air. Due to the higher outlet pressure setting, which is P2 equal to 1.4 bar instead of 1.0 bar, a greater amount of work was required to achieve the compression process. This resulted in higher energy input than theoretically expected. However, not all of this energy is effectively utilized to increase the internal energy of the air, as a portion of it is dissipated as heat to the surroundings. Therefore, the total work input is greater than the useful energy retained within the system. The second one is compared to the heat added to the air. The heat added to the air is associated with the increase in its internal energy, which is reflected by the rise in outlet temperature. Although the higher outlet pressure contributes to a greater increase in temperature, not all the supply energy is retained by the air. Some energy is lost to the surroundings due to heat transfer, indicating that the process is not perfectly adiabatic. As a result, the heat effectively added to the air is less than the total work input, with the difference representing energy losses during the compression process. For the conclusion regarding to behavior of the single-stage compressor as it heats up. So in conclusion, the single-stage compressor exhibits temperature-dependent behavior throughout its operation. At the initial stage, the compressor transfers energy to the air at a relatively high rate, resulting in a rapid increase in internal energy and a steep rise in temperature, as indicated by the initial gradient of the heating curve. However, where the temperature trend remained consistent, the recorded values were higher than expected. This is mainly attributed to an incorrect pressure setting, where the outlet pressure P2 was set to 1.4 bar instead of the intended 1.0 bar. This higher than required pressure significantly affected the thermodynamic behavior of the system, leading to elevated temperature readings of up to 207 degrees Celsius. As a result, although the overall temperature profile followed the expected pattern, the magnitude of the temperature was not in agreement with theoretical expectations. In addition, the process is not perfectly adiabatic, as heat transfer to the surroundings still occurs. Overall, the incorrect pressure setting caused a deviation in the measured temperature values while preserving the general trend of the system behavior. The speculation of the result with the condition given, which is if the compressor outlet pressure P2 is reduced to 0.5 bar. If the compressor outlet pressure is lowered to 0.5 bar, the compression process becomes less severe, leading to a smaller pressure ratio across the compressor. Consequently, the work required per unit mass of air decreases because less energy is needed for compression. As a result, the heating curve would exhibit a reduced rate of temperature increase compared to the original condition. The temperature time graph would have a gentler slope, and the final steady state temperature achieved would also be lower. Furthermore, the lower work input results in less conversion of mechanical energy into internal energy, while heat losses to the surrounding remain relatively significant. Hence, the system would reach equilibrium more quickly but at a lower operating temperature.
Moving on to the last part of the lab report, which is the safety procedure. So for the safety procedure, first and foremost, before we do the experiment, we have to do the pre-operation check, which is to ensure all connections are tight, no leaks are present, and gauge are working properly before starting the compressor. We have to wear our PPE, wear safety goggles, gloves, and closed-toed shoes at all times to protect against refrigerant exposure and hot surfaces. System setup, which is we have to set all valves to the correct position and start the compressor while closely monitoring pressure and temperature readings. During the operation stage, we do not touch hot or moving parts and do not exceed the recommended pressure limits during the operation. And if we encounter any emergency situation, we have to switch off the system immediately if abnormal noise, pressure, or leaks are detected. So for the shutdown process, we have to turn off the compressor and power supply and then allow the system to cool before handling. That's all from us. Thank you.